Okay, in the last video we looked at separable differential equations, and in this video we're going to look at one of the applications of separable differential equations. And again, I do actually stress, I've never done these before. We're doing them, they're in your textbook, and we're doing them because according to your textbook, in a lot of engineering programs, you will have to find these types of applications. They'll pop up a lot, so we're going over them just to make sure all of you are clear. The math is pretty straightforward. They're separable differential equations. It's just understanding one or two tricks of what's going on. And the idea is we want to look for what's called orthogonal trajectories. You all know orthogonal just means perpendicular. And the idea is when you're told to find an orthogonal trajectory, what you want to do is find the slope of a tangent line that's perpendicular to the slope of a tangent line of a function that you're given. Meaning, suppose we have this, y equals k x to the fourth. And keep in mind, this k is a constant, but it's arbitrary, which means this is not a function, it's a whole family of functions. And I actually took the time for a few of these and graphed them in Desmos. You can graph them in Desmos or graph them in Maple. I'm aware with the Maple virtualization, sometimes you can get timed out now because so many people are using it. But you can just graph these in Desmos. And essentially the idea is, think about these curves, x to the fourth with any constant k there. So you can see all of the fourth degree power functions like that, different values of k. You now want to find a family of functions that for any k will be perpendicular to those at any point where they intersect, meaning the tangent lines will be perpendicular. So not for the graph of this one, but just in general, if I arbitrarily had a function, let's see, I graph one in Desmos, I think I graph some hyperbolas like this. And again, this is just one hyperbola, but in Desmos, I can graph a whole family of them. So say I have another one here, or another one here, etc., etc. At each point here, I want to try to find a function or a family of functions that when they intersect this hyperbola, the tangent lines are perpendicular. So say for this one, I want to say the graph I got was something like exponential, what did the graph look like? I'm trying to draw it well. But clearly, right here where this is vertical, I would need some type of function, say like that the tangent line here is horizontal and here it's vertical. And that's what we're going for here. Given a function, find another family of functions that at any point where our new family intersects this family, their tangent lines will be orthogonal. So, as far as it goes, there's the understanding of what we're doing from a real world perspective, and then there's the actual math involved. And the math involved is, well, let's see. If that's the family I have, and I want to find a set of families that are orthogonal to it, I'm talking about the tangent lines, which means I need to take the derivative. So I take the derivative of both sides. dy dx equals, keep in mind, k is just a constant, so 4kx cubed. Now I have my derivative. The one problem is, this k is a constant relative to this family right here. The problem is, once I plug it in down here, if I think about it as just a constant, I'm essentially missing some information because that k is clearly related to x and y. And I want to make sure I don't lose information with this k, which is essentially something to do with y and x down here, when I start manipulating down here. So what we have to do is figure out what k is. In this case, if I solve for k, I get k equals y over x to the fourth, and then substitute it in over here. So now I have dy dx equals 4y over x to the fourth, x cubed. So dy dx equals 4y And then let's see, x to the fourth x cubed, so there's an x on the bottom. Now, this is the derivative in terms of y and x of this family right here. Now I want to find a family that is orthogonal to that, which means now I need to find, since this is the slope of the tangent line, dy dx, we all remember from pre-calc or whatever, things that are orthogonal have negative reciprocal slopes, which means I find the negative reciprocal of that. So now I have dy dx equals negative x over 4y. Just flip it, make it negative. You all know how it works. Now I need to solve this for y, or solve this and get y, which will be the family that has orthogonal trajectories with that one right there. So now this is the easy part. This is just solving the separable differential equation. I'm going to multiply the 4y and multiply the dx. I get 4y dy equals negative x dx. Integrate both sides. Here, antiderivative of 4y is 4y squared over 2. I know those will cancel, I'm just writing it long form. Equals, let's see, negative x squared over 2 plus c. And now in this case, I get 2y squared equals negative x squared over 2 plus c. And there's my solution. In this case, given that that's a y squared, I'm not really going to be able to solve it explicitly. Generally speaking, we try to simplify how these look. And in this case, I'm going to multiply everything by 2 and move the x squared to the left. And I'll get 4y squared plus x squared equals c. And keep in mind, I multiplied c by 2, but 2c is still a constant, so I'm just going to call it c. If you want to call it c1, you can, but it doesn't matter. And now here, I have the set of solutions. So, I'm aware these take a little bit of time to go through. I want to do one more, just so we can kind of get the idea of how they work. So let's see, x squared plus 2y squared equals k squared. Let's see, I want to find the set of orthogonal trajectories to that. That's a family of ellipses. If you don't recognize the equation, it's written in a slightly different form, but that's a family of ellipses. And let's see, I want to solve it, so take the derivative. 2x plus 2, keep in mind I'm taking the derivative with respect to x, so that's implicit differentiation. So that's 2y dy dx equals derivative of k squared. K is a constant, so that's just 0. Now, divide everything by 2 just to get rid of the constant, or get rid of the constant common 2. Then you'll have x plus 2y dy dx equals 0. Now solve for dy dx, so subtract the x, divide the 2y, and you'll get dy dx equals negative x over 2y. And now keep in mind for this one, there is no k here in my derivative, so I don't have to worry about substituting, solving for k up here and substituting. Because there's no k here, so it's completely fine, I don't have to worry about that. Now, this is my derivative. I'm looking for the orthogonal trajectory, so I flip it. So I get dy dx is equal to, flip the sign, so negative becomes positive, flip the fraction, 2y over x. Now let's see, just solve this differential equation, multiply the dx, divide the dy, and actually, yeah, in this case I'm going to leave the 2 on the left just for them to deal with the fraction. So that's dy over y equals 2 dx over x. You can do whatever you want with the 2, it doesn't matter. I'm going to leave it on the right just to make it easier on myself. Now I've separated, integrate both sides. On the left, antiderivative of dy over y is ln y equals here. The 2 carries along, antiderivative of dx over x is ln x plus c. Now I want to solve for y explicitly, so do e on both sides. E to the ln of y is y equals e to the 2 ln x plus c. Now I'm going to kind of manipulate this. I'll have y equals e to the ln x squared, rules of exponents, raise an exponential to a power, multiply the powers together, which is all that is, times e to the c. Multiply two exponents together, add the powers, so we're completely good. Now, this is y, e to the ln cancels, and this becomes x squared. E to the c is just a constant, so I'll stick it out in front. Y equals ax squared. And now here is where, again, if you want to throw these into Desmos or Maple or whatever you have available, you can do that. If we think about the graph really quickly, let's see, that's x squared over k squared, that's twice as big, so it'll be half as big, so that one will be bigger. So these are horizontal ellipses centered at the origin. So they kind of, up to my ability to draw, that's one of the ellipses in the family. Over here, these are quadratics centered at the origin, which means they would look like this. And the idea is, again, this is a rough sketch, right here where they intersect, the slope here goes that way, the slope here goes that way, and those two slopes are perpendicular, and that's the idea. The biggest trick to these is making sure you do all the steps correct. Given the family you care about, take the derivative with respect to x. If necessary, substitute in for k. Then solve for dy dx. Then take the negative reciprocal so you can get the orthogonal ones you care about. Then separate, do the easy part, which is the integration. And then, if possible, you'll get the implicit solution. If possible, algebraically try to get the explicit solution. And then if you're so inclined, you can check by graphing, and it appears to actually work. The one thing I would point out, and I say this because I was discussing it with the other math instructor, there are some mistakes in the NCE State book that you're using for this class. So do not assume just because you get an answer different than some of the answers listed in the book that you're wrong, because there are some mistakes in there. We actually went through them and checked them over the weekend. I would say the best thing you can do is, if you get an answer different from the book and you're convinced you did it right, go into something that graphs, Desmos, Maple, whatever you have, graph them and see if it actually works. That solution to this, just rough sketching, clearly looks like it is working. And it should be obvious when you graph them if your solution is correct or not.